Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we're continuing on our star formation idea by looking at the nature of protostars. Protostars are the early seeds of stars before stars become what we call stars. So what exactly does that mean? It means that stars have a birth, they have a life, and they have a death. And they form in clusters of stars in great clouds made out of the giant molecular clouds that we saw before. They form in star clusters that appear in H2 regions and ionized gas regions filled with pillars of gas and dust. And as they form into these groups of stars, many of them, before they shine with the light of fusion in their cores, they contract under gravity and form protostars. So let's look what that means. So once again, we look at the sun, and we're going to take this with respect to the sun. The sun is very, very, very old. It's about 4.6 billion years old. And that's how old it is. And today we find it's in hydrostatic equilibrium, which means that the pressure from within that pushes the hot gas out from the center is balanced by the gravity pulling all the gas together. That's funny to think that stars are made of balls of gas and they're totally gaseous. But yet, when people think of that, they say, well, gas doesn't have gravity. Well, of course it does. It's matter. So gravity pulls all things together. It doesn't matter what the matter is made out of, whether it's gas or liquid or solid, it pulls it together. And then the pressure at the core of the star balances it. And that balance is what we call hydrostatic equilibrium. And it's hydrostatic because the gas acts as a fluid. And we also say that stars are in thermal equilibrium because in the center of, say, the sun's power is by fusion reactions, and that fusion reaction provides the energy that keeps the pressure going against gravity. And so that energy then slowly makes its way out to the surface and emerges as light. And that, however much light comes out at the surface, that's what's actually being produced down in the core. Well, without taking into account, say, the neutrino loss, but we've got the luminosity is basically the luminosity of light and luminosity of neutrinos, add that up together. And all that must balance out the energy that's that's produced in the core, must be the amount of energy that's leaving the sun. And so how did it get that way? That's the real question. And so there's two steps to star formation. The first formation is to form a protostar. And then that is a hydrostatic equilibrium phase where pressure is balanced against gravity. And then you form a thermal equilibrium phase where the energy that's coming out of the surface is balanced by what the energy being produced in the core. And that's pre-main sequence. So we're going to look at the protostar formation phase as well as the pre-main sequence phase. So where do we see these things born? We see them born in star clusters like we've seen around. Now we know that they're formed because of looking at the interstellar medium, and we looked at H2 regions in the previous lecture. And we also looked at giant molecular clouds. Those things are enormous clumps of gas and dust, about a parsec or so, 1/10 of a parsec in size, and they may be larger. And each of these things are about a few solar masses in size. And these clumpy giant molecular clouds have a very, very high density, and they will collapse under gravity. And so as they collapse under gravity, the most dense ones collapse first, and they collapse fastest. And as they collapse faster and faster, the pieces of them that are more dense inside the clouds collapse into other clouds, and those things rip apart inside the cloud and form little clumps that then form groups of stars. So let's begin with the concept. So there's our basic concept. You have a big, 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 big cloud, an interstellar cloud. Something comes along and causes it to contract. Maybe it's a little bit more dense in that region. Maybe there's some shock that comes along, and we saw in previous, something counterbalances the motion of the gas and the magnetic field from the turbulence of the gas, and it starts to collapse. And as it collapses, it fragments from one side of fragment into the next. So it makes a bigger fragment, and those bigger fragments turn into littler fragments. And so now the littler stars, or little fragments, come from the bigger fragments. So you got quarters them and quarters them again. And at some point, they get to the point where the density is high enough that it actually can't fragment anymore. So it's kind of like thinking of teardrops being pinched out of a thing. So they pinch in those little nodules, and it pinches them apart. Once you get to under a certain density, it's not going to fragment anymore. All right, so then you get these adolescent young stars. The interior of the fragments begin to heat because as they collapse, any gas that you compress warms up and gets hotter and hotter. And so they're collapsing under gravity, and eventually they form the surface that's about 10,000 Kelvin, and that is the surface of a protostar. So why do they actually collapse? Because in general, when we look at individual atoms, they're moving pretty fast in these big clouds. And they move fast enough that sure, they might get close enough together that they actually could collapse, but they have enough kinetic energy that after they get close together, they spread apart. So something has to come along to actually keep them together. They have to cool off by emitting light. And that's the thermal loss. That is the loss of energy. So once they get to that collapsed value, if there's no way for them to emit the energy that they have in kinetic energy, then they just keep going. But if they somehow interact with each other, and there's various processes by which they can interact, the electrons can interact, the protons can interact, they can stick and form molecules. There's many ways that they can interact and thus lose the kinetic energy. So if there's some way for them to stick together, then they can, and then they'll allow them to contract in a lump. Otherwise, they would spread apart. Well, there's a lot of different stages that they can go through. This is a nice, helpful way of determining what rough area it is and how big they are, what their densities are, and how long they're in these phases. Once a star starts to collapse out of a cloud, it takes about 2 million or so years or a couple million years for the star cloud to collapse. It's extraordinarily cold in the center of it and extraordinarily cold in the surface, and it pretty much has almost no, it's only about 1,000 particles per cubic centimeter or a billion particles per cubic meter, and the diameter is enormous. It's on the order of a few light years. Now, when they start to collapse, the central temperature rises a little bit, and it lasts, and the central temperature is a fragment. It's that first fragmentary sec. The density raises by a factor of 1,000, and it drops by a factor of 100 in terms of diameter. And it's really in basically free fall. So we can think of the cloud fragment as free fall. And then, so when the core temperature reaches about 10,000 Kelvin, that can balance against the gravitational pull. And now we're in hydrostatic equilibrium. And that's the first element of a protostar. The protostar then balances out at that third set. The density is increased by a factor of 1,000,000, and the diameter is again decreased by a factor of 100, and now we're about 10,000 degrees in the center. That lasts for about 100,000 years or so. And then about 1,000,000 years more, for something about the size of the sun, it'll be a protostar. And the protostar means the collapse that occurs gets emitted in the form of light. And so the central temperature is about 1,000,000. We still do not have fusion happening in the core, but it's just incredibly hot. It's wildly dense. It's now 10 to the 15th times more dense in the core than it was when it was a cloud. The diameter is contracted by a factor of 1,000,000, and the surface temperature now has raised to the surface temperature of the coolest of stars. And then about 10 million years, the sun would have lasted with a central temperature of about 5 million degrees, and the surface temperature rose up a bit, the central temperature raised even more, and then you had a period where deuterium fusion is occurring because that's all the temperature you need to just fuse whatever latent deuterium is in the core in order to supply the energy that's seen at the surface to balance against the gravity as it collapses further. It takes about 30 million years to get to the next stage, which is its first zero-age mean sequence time. It'll go down to about 10 million Kelvin, where deuterium burning becomes much more prevalent throughout the entire core. A core structure develops, an envelope structure develops. There is not much left around the star. The protostar envelope is now gone, and the star itself is revealed as an individual object, and the central temperature is incredibly hot. Incredibly dense. It's 10 to the 22nd times more dense than it was as a cloud. The diameter now has shrunk down to the size of a typical star, about 1,000,000 kilometers across. And then the last stage is the main sequence lifetime of the star. For the sun, it will last about 10 billion years, where full proton-proton chain fusion reactions occur. So if we just look at the stuff from stages 1 through 6, we see that it collapses from a cloud into a fragment. It balances itself, the gravitational pull balances itself by the heat coming out from the center, and the protostar itself goes through 2 phases where it's incredibly hot in the center, but not yet fusion hasn't started, and then finally deuterium-only fusion has started, but it's not hot enough for a proton to intersect with another proton until the core temperature is about 15 million Kelvin. So how do we make protostars? Well, protostars start out of these cores. Remember we saw like the evaporating gaseous globules in the Eagle Nebula? as well as in the Trifid Nebula and all over the place in these dense star-forming regions. The cores start out as low density. They're kind of transparent, mostly transparent. Photons get out, and that keeps the gas cool. Remember, that's how the gas can actually collapse, is that the light has to be able to get out such that you can still keep collapsing. But there comes a point where it becomes opaque, and then the light gets trapped. So then the gas starts to heat up. Then the pressure starts to build up because the gas is heating up, and that's the old that is the normal PV equals NKT, which is the ideal gas law. Pressure builds up, and that becomes hydrostatic equilibrium because now the pressure balances against the gravity because it's become dense and hot, and none of the light escapes. So it becomes basically like a big ball of opaque gas. So now the protostellar core continues to grow because stuff flows down into the core. Gravity is still working on it, and it's not that it stopped collapsing. It's that the core is growing because material in the surrounding cloud is simply too opaque to actually let the light out. Now, the protostar phase, as we've discussed before, lasts only up to at most 100,000 years. And it's got this temporary sort of hydrostatic equilibrium because this isn't going to last long because there's stuff raining into the core from outside, but it's still balancing the pressure versus the temperature is from the outside, and it remains deeply embedded inside of the parent gas. Now, this is a short-lived stage in the star's life, very, very, very short-lived stage. And short-lived means they're hard to find because when you do go try to find a protostar, you have to look in very, very special places because if something lasts a long time, it's easier to find and there's more of them. If something doesn't last a long time, there will be innately fewer of them around. And since protostars only live a short period of time, that means they're hard to find in the sky. Protostars themselves have disks. As they rotate, they have a preferential rotation to the gas, so that actually collapses along the rotational axis, and then matter can fall along the poles of this rotation axis of a big disk, and then matter along the equator falls slowly in because it's rotating around, and so it'll take time for it to lose that rotational energy. So it can fall along the poles, but it'll spin along the equator. And the result is that the infalling gas looks like pancakes. So you get these flattened disks around the equator of a protostar. But eventually, the protostar forms and becomes so hot that the disk of material starts to become cleared away. The heat and energy from the light pouring out from the young baby star becomes incredibly intense and destroys the outer areas of the disk that surrounds the baby protostar. Then, as the disk forms, some of the matter falls onto the remaining star, and the rest might form planets. And in fact, the Kepler Space Telescope, one of the most important results in the last 10 years, is that the Kepler Space Telescope has found that pretty much every star in the sky has planets, so these protostellar disks form planets all the time. In fact, it's very seldom that they don't. And so observations in the sky show that these disks get cleared away in a few million years, and then the dust grains and little pebbles and rocks take a lot longer because those things get cleared and turned into planets, and they become comets or asteroids or just basically zodiacal light that we see around the Earth. And these dusty debris-ridden disks are frequently found about young stars. So how does a protostar then become a star? Well, they shine because they're hotter than their surroundings. Remember, the rest of the stellar nursery is just a big cloud of gas and dust. Now, protostars are really, really hot in their cores, and so they emit an enormous amount of light in infrared or visible light, depending on the surroundings. Now, the energy source, they've got to need an energy source, but can't do nuclear fusion in the core in order to stay hot. That energy source is gravitational contraction. So as the protostar shrinks slowly, it releases the gravitational energy in the form of heat, which then gets radiated in the form of light. So you take a big cloud, let it collapse under gravity, it gets hot. When things get hot, they glow. And by hot, we can even mean 100 Kelvin or 200 Kelvin or 1,000 Kelvin. And that gets enough to release the gravitational energy in the form of light. Half of this energy goes into photons, and the other half goes into heating the core. So some of it doesn't come out because it's dense enough in order to make the kinetic energy of the atoms and molecules go in no longer molecules because it's too hot for molecules, and no longer hot for atoms because they'll be all ionized in the core, and the rest of the core becomes heated. So how long can it do this? Well, the reason it can only do this for a very short period of time, comparatively speaking, and we call this the Kelvin-Helmholtz timescale. And that's how long something can shine only by gravitational contraction. And this is something we talked about when we looked at the age of the sun, and this is the exact process that Kelvin and Helmholtz tried to use when people did not know that nuclear fusion existed. So this time scale basically says the gravitational binding energy, which is the mass squared divided by the size of the object, radius squared, and you compare that to the luminosity. So the m squared over r, now where does that come from? Remember, the force due to gravity equals the Newton's gravitational constant times the mass of one thing times the mass of another thing divided by the distance between them squared. But the energy that's obtained by something falling in a gravitational field is simply the force times the distance through which it falls. And g is just some constant. So really we have the self-gravitation of the object is just the mass squared of it, because it's all gravitating on itself. It's just self on self, so mass on me. So the two masses are, well, itself. So you can think of it, the gravitational force can be multiplied by the size of it to give you just an m squared over r. Now that's an energy then, because the energy you get from things falling by gravity is simply the force due to gravity times the distance through which they fall, and we can think the distance through which they fall is simply the size of the object, and that gets you the m squared over r. Now that energy gets radiated, so the L is luminosity, energy radiated per second. So if you take the gravitational potential energy, which is proportional to the square of the mass of the object divided by the size of it, and then you divide it by the luminosity of it, you get a characteristic time scale for it to emit all of its energy. So one solar mass might live about 30 million years as a protostar, and the higher the mass, the shorter the time, because the luminosity is much, much greater for higher mass objects. So the mass squared over r is roughly the same for most stars, when you're talking even one solar mass or half a mass up to like 10 or 15 solar masses, but the luminosity goes up a lot. It goes up by factors of a million or 10 to the fifth between these small stars and these big ones. So the bigger they are, the more massive they are much, much, much more luminous for a larger mass. So the mass squared over r does not rise as quickly as the luminosity. So the Kelvin-Helmholtz timescale is shorter for more massive stars. All right, so this kind of shows the tracks that they do, and we thought about the idea of an evolutionary track, or where the star appears on the main sequence as a function of time. So we can have a big, big, big cloud, which could be a range of starting luminosities and masses, and if it's a little bitty star, it'll start off fairly luminous, maybe much more luminous than the sun, and then as it contracts, it will get smaller and smaller and smaller, and less luminous because it's physically smaller. A star like the sun will contract much more quickly and it'll have that kind of kinky loop in it, and that's because deuterium burning is occurring. Once it gets to that loop, even more massive it ends on the main sequence higher and higher and higher up. So we look at a 15 solar mass, it has incredibly short time scale on the order of tens of thousands of years to form from a cloud down to a hot O and B type star. But a little bitty half-mass solar star will take hundreds of millions of years, if not even longer, for it to reach the main sequence on these tracks. So the length of time on each of these tracks depends on the mass. So the 0.5 solar mass thing will take a long, long, long time to run that arrow, but a 15 solar mass star will rip across that arrow incredibly quickly. And so that's why we see in star clusters and star birth regions, we see the brightest, hottest stars forming first, because they form before the cloud gets used up or gets dispersed. But the little tiny ones are prevalent everywhere because they take a long time to form, and they keep forming and forming and forming and collapsing, and eventually they get formed, but not until all the big stars are dead. So high-mass protostars, as I said, a 30 solar mass protostar collapses in less than 10,000 years, and the collapse proceeds. The core gets very hot until it reaches 10 million Kelvin, and that ignites the proton-proton chain. But in very massive stars like 30 solar masses, it'll immediately go into the carbon-nitrogen-oxygen or CNO cycle in its extremely hot core. And when it does that, those hot stars ionize the remaining interstellar medium, create those H2 regions we talked about last time, and they completely destroy all of the remaining gaseous areas, forming what we saw last time as a Stromgren sphere. That's what high-mass protostars do, and they go really fast. The lowest mass protostar, though, takes a long time. Something about the mass of the Sun takes about 2 to 10 or tens of millions of years, and something 2/10 the mass of the Sun can take up to 1 billion years to form. So there are some protostars that have just started forming that actually only just formed 1 billion years ago, or 3 billion years ago. The Sun's about 4.5 billion years old, but yet some of those stars formed well after the Earth was formed, well after all the planets were formed, and even well after the first emergence of life on our Earth. So even after the Sun was formed and all the planets were formed, there were still little M-type stars that were from the nebula out of which the Sun formed that still hadn't formed before life formed on Earth. Now eventually, for just low-mass stars, that when the core temperature gets to about 10 million Kelvin, that's when proton-proton chain fusion, and that's what we talked about in the Sun. And the stellar wind also then blows away the cocoon that surrounds it, and there's a remaining disk, and it's gone, and then it becomes a main sequence star. So the end of the protostar phase is the main sequence phase. And what we call that the zero-age main sequence, or ZAMS, which is a great thing. ZAMS, zero-age main sequence. The core heats up, hydrogen fusion runs faster and faster. That's where that little kink is in those tracks. And the core temperature rises and the pressure rises, the collapse slows down, and finally it gets into a total balance where pressure inside equals the gravity outside. That stops the collapse. But until the luminosity of the star is balanced by the energy that's created in the core, you don't have thermal equilibrium. Once both of those have been achieved, hydrostatic equilibrium by pressure balancing gravity, and thermal equilibrium with proton-proton chain providing the energy that's being lost by the luminosity, then you have what's called a zero-age main sequence star, and it lives on the main sequence now for the Sun for 10 billion years before it starts doing things different. Now the smallest mass that you can possibly have for a star is about 8% of the mass of the Sun. Below that mass, it's never hot enough to ignite proton-proton chain or CNO cycle type hydrogen fusion. And we call those things brown dwarfs. And brown dwarfs are just literally only a little bit bigger than the planet Jupiter. And we call them super Jupiters because their properties are really weird. They do generate energy because of the Kelvin-Helmholtz mechanism by contraction under gravity. There's now significant numbers that are known because of the Wide Field Infrared Survey Explorer, which is the WISE telescope, as well as others like the Spitzer Space Telescope has been able to discover many of these. And they shine almost exclusively in the infrared, and those are what we call the T-dwarf stars. They are remember we had the OBAF, GKM, L, and T, and the T-type dwarfs are the brown dwarfs. They're just not much bigger than Jupiter's. And so here's an image from 1995 on the left from the Palomar Observatory looking at Gliese 229b, which is a brown dwarf orbiting a star. It's just a stellar companion, and it's emitting its own light. It's hotter than Jupiter, right? So it's a star, but it's a brown dwarf. It's not really a star. It doesn't do fusion, so it's a brown dwarf. And the Hubble telescope took a wide field view of it with the Wide Field Planetary Camera 2, or WIFPIC 2, and observed this thing, which is a very close by brown dwarf type star. And just to give you a comparison of the sizes of them, we looked at the Sun, which is that disk on the left, which is too big for the screen. And we have Barnard star, which is that nearby star with a high proper motion. And Gliese 229 is the little bitty brown dwarf, or Gliese 229b as we would call it, is a brown dwarf that's only physically a little bit bigger than Jupiter, but its mass is much greater than Jupiter. So it is shining by gravitational contraction, much more massive than Jupiter, but much more dense than Jupiter. And to give you a comparison, there's the Earth. So those little brown dwarfs, they're intensely hot. So if you got close to one, really close, you'd say, wow, that looks like a star. But you have to get really close in order to say that's a star, meaning you have to be orbiting it about the same distance that the moon orbits the Earth. So they're really kind of dim. In any event, Gliese 229 is one of the many brown dwarfs that are known. There's also a maximum mass. Once it's above 100 to 150 solar masses, is not really well known what this is. But the core gets so incredibly hot that the radiation pressure, meaning the pressure from light itself, is too strong for the gravitational pull, and it gets so incredibly hot and the radiation is so intense that it actually rips the star apart. And the star becomes unstable. It kind of looks like a lava lamp. There are some examples of such massive stars that literally are disrupting themselves off, and they shed huge amounts of mass until they finally get themselves below 100 solar masses, but they live such a short period of time that it's a race between shredding themselves by radiation pressure or exploding in a supernova. There's really not really a fantastic, well-known amount, but it's called the Eddington luminosity, and the Eddington luminosity is the maximum luminosity that a star can have before it rips itself apart by light. So what do we see out there in the sky? If we look out into the galaxy, there are stars of all different kinds, where we've seen OB-AF-GKM type stars all over there, and Ls and Ts out there, and we see them in all different life cycles. Now, if the phase is long-lived, meaning maybe it lasts billions of years, then we'll see many stars in that phase because there's many more opportunities for a billion years to intersect today. If the phase is extraordinarily short, say 10,000 years or so, we will only see a very few stars in that phase because the probability of a star in that phase being in that phase is very short compared to small compared to that. Now, the pre-main sequences phase is longer because of the longer Kelvin-Helmholtz timescale, so we're going to see mostly low-mass protostars if we see protostars. But actually finding a high-mass protostar is extraordinarily difficult because the time frame is very short for them. But the main sequence phase is what we see most stars in the sky. Almost every star you see in the sky is a main sequence star, except for the supergiants and giants. So 80% of the stars in the sky that we see, 70-80% are main sequence. And since that phase is extremely long, we see more main sequence stars in the sky than giants. We also see more main sequence stars than protostars. How long's the main sequence phase? It just depends. Depends on this type of star we're looking at. And if we look at the types of stars that we can actually observe in the sky, it's all dependent upon the nature of their masses. Low-mass stars, low-mass protostars, which are in the lower left, as they begin as tiny, tiny protostars, they become brown dwarfs, and they stay brown dwarfs. Once a brown dwarf, always a brown dwarf. They don't do anything else except that. Well, that's kind of like a Jupiter sort of thing, a super Jupiter that we saw like Gliese 229b. More massive protostars become red dwarfs, which are M-type stars. And M-type stars stay red dwarfs for a very long period of time. They might swell up a little bit as they age, but eventually they run out of fuel and become white dwarfs. Stars like the Sun in their protostellar phase live as main sequence stars for about 10 billion years or so. Oh, and red dwarfs, they last about 1 trillion years or so. So there are no red dwarfs that have ever become white dwarfs in the history of the entire universe. A star like the Sun lives 10 billion years, it becomes a red giant and a planetary nebula. And stars a bit more massive than the Sun, up to say about 8 solar masses, also become planetary nebulae, become white dwarfs. Then stars that are much more massive, like say 8 times the mass of the Sun, become blue supergiants, then become red giants, then expel huge amounts of material as a blue giant, and go into a supernova phase, which we'll talk about in a few lectures. And they explode, leaving behind a neutron star. Much more massive protostars form exceedingly quickly and live a short lifespan of only a few million years before they explode catastrophically as a supernova and leave behind a black hole. But the most massive stars in the 100 solar mass category become blue supergiants, and they don't even really leave behind a remnant. When they collapse, they might have all sorts of material flowing out of them as part of their life as they shred themselves under the radiation pressure. But when they collapse and die, they just go whoomph into a black hole and they're dead. They don't even explode as a supernova, the most massive stars. So the only material that gets out of them is from a large, large shell. But if we look, then we see that there's a process of clouds collapsing on the left to form protostars. Then they live their lives. And some of this material goes out to make clouds in the cosmos, and we could easily link the right-hand side of this image with the left. And if we do, we find that stars cycle through clouds and into protostars and then stars and then back to clouds. From ashes to ashes and dust to dust we go, as the phrase is. So stars like the Sun are formed when a cloud of dust collapses under its gravitational force, collapses, and its center becomes hotter until fusion begins. And that's our classic idea. Eventually, it forms planetary disks that form planets, and at the end of the course, we'll talk about planetary formation. and planets themselves. But we're mostly concerned about the formation of protostars into pre-main sequence stars. And we've seen this before when we looked at the giant molecular clouds as well as the H2 regions. We see that such baby stars, such protostars, exist in great profusion in, say, the Trifid Nebula. This is from the Spitzer Space Telescope on the right, from NOAO, picture with Hubble insets on the left, and the arrows point to the protostars. But these little tiny protostars are little tiny M and L and T type stars that emit only in the infrared. In fact, on the visible light image, we don't see them all, so these would be L and T type dwarf type stars, or protostars inside of their embryonic cocoons and still have not emerged. And we also saw that in the Eagle Nebula, there were starbirth clouds, and each of these clouds make these evaporating gaseous globules, and we see these little nodules and lumps, and inside each one of those nodules and lumps is a tiny baby star in the process of being formed out of the collapsing cloud. So it's not as pretty or even as symmetric a concept as we could possibly imagine. This is a messy, messy, messy concept. And each of those nodules that we see in the top of the screen, those things are about 100 times bigger or more than the entire solar system. Whereas the cloud itself that we're looking is about a quarter of a light year or half a light year or about a light year across, somewhere on that order. And the light that's emitting and the gas that's coming off of it is because of the hot O and B type stars that are well above it. If you go straight up in this image, you would get to a hot O and B type star that's emitting so much ultraviolet light that it's literally evaporating this stellar gas cloud. And so as it evaporates, the dense regions get exposed, and those are where the baby stars are forming. And we see the effect of the baby stars forming, and we see jets inside of them. So on the left-hand side, this is from the 2014 revisit of the M16 Nebula. We're looking at on the left-hand side, about a 2 light-year long cloud. And we can see the effects of the baby stars on their surrounding environments. And on the right-hand side, we see a very, very clear jet from one of these nodules that's kind of sticking out towards us, but there's kind of an up and down jet on the lower right area, and a motion of some other jet in a more embedded and more difficult to see cloud in the upper left. But there's this bipolar jet from some baby cloud, some baby star. So let's go get closer to see what they're doing. First, let's look at track of a star on the HR diagram. A protostar ends up being an extraordinarily luminous object. Something like the Sun, when it was formed as a protostar, would first be at least 100 times the radius of the Sun as an object, and would be extraordinarily luminous. It'd be about 10,000 times the luminosity of the Sun for a while. And that means that since it's pouring all this energy out, it can't do that for long because, well, it's not doing fusion in the core yet. So that energy is pouring and streaming out of it. And it's also serving to heat up the core as well as being radiated by light. And protostars, of course, are not in equilibrium because we start from these big clouds. They collapse down into very, very tiny objects. And the time frame that we're looking at to get to a protostar through the protostellar phase, which is in the latter two sides, from cloud to fragmentation to baby protostar to pre-main sequence star, takes tens of millions of years or so. So that stellar phase that we looked at, it drops down towards the main sequence as it collapses because the luminosity drops as the radius drops, because there's lower surface area from which it can radiate. So therefore the luminosity drops. Now as the luminosity drops, the temperature doesn't change too much. It gets a little bit warmer on the surface, but the core is rapidly increasing in temperature. It's also becoming much more compact. And then when we get down to the lower area where it gets that hook, it starts to get a little bit more luminous because deuterium fusion ignites deep in the core when it reaches 10 million Kelvin. And that's a form of nuclear fusion. That's just eating up the latent deuterium that was in the cloud from which it formed. That's the protons merging with the deuterium, but that's a later stage in the proton-proton chain that was very easy to do. The big tough thing is the proton-proton chain, and this is serving, the deuterium fusion is serving to heat up the core of the star more, but it's also starting to try to make the star balanced, and it pushes the star along the track, and eventually it gets to the zero-age main sequence when it gets hot enough in the core and compact enough in the core for it to be about 15 million Kelvin, and when it does that in the core, then proton-proton chain nuclear fusion can occur, and the surface temperature is about 6,000 Kelvin, and now we've got the Sun. And that whole process along that track took about 10 or 20 or 30 million years. And we can see this out in the sky by looking again at these big, big, big clouds, and the collapsing clouds then get evaporated as the stars are formed. And here's what a disk might look like around a baby star as it's forming. As it forms, the disk collapses down into this structure like this, and some of the material keeps falling into the star, giving more mass to the star from the disk. And there's a magnetic field associated with the rotation of the star and the energy of the ionized portions of the star. So there is a jet-like structure that is seen from the rotational aspect of the entire system, as well as the growth of a very powerful magnetic field. And material can get entrained in that magnetic field and shot out at extraordinary energies because it does not lose the angular momentum. It just simply spirals along those magnetic field lines. And if we were to go deep inside some dark cloud like Barnard 68, we might see something like this, with a protostar with an accretion disk around it, embedded inside a dark, dark, dusty cocoon, and each one of those dark, dusty cocoons probably has a protostar baby inside it with jets popping out. And that's what we see here, protostellar jets. And this is in a dark dust cloud called BHR 71, taken by the Spitzer Space Telescope. And so the VLT image, which is a very large telescope, a European Southern Observatory, and then it can be matched up against the Spitzer Space Telescope, which are infrared, and you combine them together. The infrared image in the middle shows the jets and exposes the baby star in the middle of it. And we see in the visible light image that it's punched its way out the backside, outside one side, so we can see the jet coming out. But the baby star has formed that protostar disk, and the jets are coming out from it. So this is possibly what might happen in the core of Barnard 68 in a couple of million years. We also see such jet activities in this amazing view that was taken by Hubble Space Telescope on the 20th anniversary of the Hubble Space Telescope in 2009, when they were looking for specific jets that after the final Hubble servicing mission in 2009, they called it the Castle of Wonder. But these gaseous pillars are in the presence of other hot stars in the star-forming region on the left-hand side, which is the visible light in the Hubble palette that we've come to see many times. And there's lots of jet-like structures. In the infrared image on the right, we can certainly see the warm gas and dust that's entrained inside these jets, and we also don't see much emission from infrared from these nodules that are containing all of the jets. So just look at the top one, way at the top of the image, and we see a jet poking out either side and a very dark nodule that just has a light glow around it because the surface of that is glowing in the infrared. But the jets themselves are extraordinarily warm and glowing in the infrared as they shoot out from these baby stars. We can also see from this that the sky is littered with dim red infrared emitting stars, and that's what we see on the right, which are not bright enough to even glow in visible light. So the visible light stars appear on the right-hand side, but the infrared cool L and T and stars do not appear on the left-hand side because they're dim and cool. So if we look at other kinds of protostars and zoom in, the Hubble Space Telescope is fully capable of actually finding and zooming in on these things. And when we look at them, these high resolution or at least high magnification objects, we get down to the point where we're seeing individual pixels on the Hubble Space Telescope's detectors. And each of these things are called like Herbig-Haro objects, which are basically young stellar objects. And they're highly variable, they change brightness frequently, and if you're an amateur observer or a variable star observer, young stellar objects are an amazing, amazing treasure trove of wonderfully variable objects. So they're also kind of tiny. And the one on the upper left, Herbig-Haro 30, looks kind of like a donut or a bagel, or a hamburger, I guess. I guess it kind of looks like a hamburger with a toothpick sticking in it. But the disk is in the middle of it, and there's a bright emission of dust that's happening above and below. But the disk is incredibly dense and not letting any light out. But we see the jets emitting from either side. Now, the disk itself is extraordinarily large and is about, remember, the 100 astronomical units is about as far as the Voyager spacecraft has gone since its launch in 1977. So half the width of one of those bars is how far the Voyager has gone. So in theory, if the Voyager was an ultra-hot object, it could be seen to have moved from the center if it were there, but it's not. You can see the dark bands, especially in the upper right. The upper right one shows the disk is so incredibly dense that it doesn't let any light out. And we see jet-like structures in the lower left, and then we see contamination by a foreground star. And there's a pair of stars. We do know stars that form in close binaries, and so here's a close binary in formation, where the upper star in the lower right image is already blown away its cocoon, but the lower right star still has that hamburgery quality with the disk around it, and the jets have been quenched. And here are many, many, many other young stellar disks, and these are taken with the Hubble Space Telescope with the NICMOS instrument, and these are all taken in infrared. You can see they all show evidence of a bright core surrounded by a disk of material with evidence of lots of outflow as some of the material gets ejected, but much of it starts to fall onto the star itself. Specifically, if we go back to Herbig-Haro 30, we find that the jets actually can be seen to be moving from year to year, and these circumstellar jets can actually be tracked over the course of years. They don't take long to actually see their changes. In fact, Herbig-Haro 47, that was taken by Burroughs and Hester and Morse in this image, that was released then, they went back and looked at it years later and found that significant fractions of these jets had moved in such a way that it's easily measured by revisiting with the Hubble Space Telescope. Here we see a hot gas bubble emitted by another kind of young stellar object, the protostars in the lower left. It's a binary set of protostar, and that's being emitted in kind of these globule sort of formats that get ejected out. And we can see that they're being ejected by hundreds of astronomical units over the course of a few years. That's an enormous speed. The outflow is incredibly fast at 300,000 miles per hour. It's not just a little wind. It's not just this puffy thing. That's pretty fast winds. It would make a hurricane look like a breath of fresh air or a mosquito's wings. But because of this, these are extremely variable objects, and the name XZ Tauri indicates that it is a variable star in the constellation Taurus that has been noticed and observed by amateur observers as well, because XZ indicates it's one of the brighter ones. Here's an incredibly good one, Herbig-Haro 24, which shows the double jet structure of the protostar still being embedded inside of its nesty cocoon. And we can't directly see the protostar itself because the dusty disk has not been blown away. But the jets have certainly carved out an area along the rotation axis. And there again, we go back and look at the stellar jet in the Carina Nebula. We see a specific object, a young stellar object, in visible light on the top. This is again another 2009 image by the Hubble Space Telescope with the Wide Field Camera 3 and the infrared image on the lower portion. We definitely see the jet-like structure puncturing out of the ghostly gas that's just warm enough to emit in infrared. But the jets themselves are extremely warm and show up brightly in infrared. We get this kind of flow where we start with a cloud that's collapsing, but it has some preferential rotation, just a little bit, and that just a little bit rotation causes it to collapse, but it can't collapse along where it's spinning. So it gets flung out a little bit along the rotation axis, and so it can't collapse radially except along the axis of rotation. It can't collapse in from the disk, but it can collapse along the rotation axis to form a disk. And as it forms that disk, then that disk gets denser and denser and becomes more and more and more ionized, which creates a strong magnetic field. And as material falls onto the protostar, some of it goes into the outflow, and that there's a bunch of dusty envelope that still exists around it. And the violence of the outflow eventually rips apart the envelope and it reveals the star inside. Some very, very young stellar objects. One of the brightest stars in the sky, in the southern sky, Beta Pictoris, the second bright star in the constellation of Pictor, was taken by the Hubble Space Telescope in 1998 by Schultz and Heap et al. With Wide Field Planetary Camera 2. And we see a dusty disk surrounding this star, and we can see that the disk itself, to show the solar system by size scale, is much, 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 much bigger than the entire solar system. So these dusty disks can be quite large. And we even go and look for protostars in the Orion Nebula, which is the most prominent, easy-to-find nebula with binoculars in the sky. And we find these dusty disks throughout the entire nebula, illuminated because the gas of the nebula is illuminated by the hot O and B type stars. And then when the little bitty protostars, the dense disks, are formed, they can show up as dark patches with a bright red core in the middle, with the protostar forming inside of them, or the pre-main sequence star in the center, with a protoplanetary disk around them. And some of these protoplanetary disks are almost completely shown. And if they're too close to the center of the star nebula, then they will become evaporated and they kind of look like tadpoles. But the jets try to form as they shoot one way, and if the jet can shield the star, before the O and B star explodes, it can form actually a shield, which allows the protoplanetary disk to get bigger. And that's kind of the upper left one. But then we look at the lower left one. That one's being ablated. Its jet would be oriented the wrong way. So the disk is getting eaten away, and so it gets warmer, but the disk is going to get destroyed. So we see that these planetary disks can come in all sorts of rotations, and the streams of particles that come out from the trapezium stars, as well as the hot ionizing radiation. There's a big race against time for these disks to form against the irradiation of the O and B stars of the trapezium, the 4 core stars of the Orion Nebula. And here is an incredible view of some really tiny young stars, and each of these would be called protoplanetary disks, or proplyds, which is a really funny thing. And at that distance of about 1,500 light years, this image is only about just a little less than a quarter of a light year across. So we're seeing 5 little protoplanetary disks inside an area that's about a quarter light year across. And that's the beginnings of a very loose star cluster. And if we zoom in on a particular one, we see a protoplanetary disk silhouetted against the Orion Nebula. It typically isn't green, but that's again the Hubble Space Telescope palette, which is mostly hydrogen in the background. They just call it a green because it makes the redness show up more easily in the protoplanetary disk. And we can get even closer to get down into the tiniest fractions of the area of the volume of it by looking at the individual pixels of the Hubble Space Telescope. And this material has a huge amount of material, almost 8 times the diameter of the entire solar system. So our entire solar system can be packed into 1 or 2 of the, or 3 or 4 of the pixels in the center. And this particular starbirth field is approximately 1,500 light years away. This is the Orion Nebula, which is easily visible in telescopes. And this is only about less than 1 million years old, maybe a few 100,000 years old. And we can actually see the very beginnings of planets being formed around other stars in dark, dusty patches. And there it is, that tiny little thing embedded inside the Orion Nebula, and that's what we call a protoplanetary disk. And they're in scads. You hunt around inside that thing, you see gazillions of them inside the nebula, because the Orion Nebula is a star-forming factory. And you can see all of them have these disky structures. And remember, the Kepler Space Telescope showed us that there are basically planets around every star, so here are the disks that one day will become planets in these stellar systems. So there's what we mean by that image, and that's where that artist's image comes from, because no one's ever seen one this close, and no one ever seen one high resolution like this. But this is the image of the artist's conception of what it might look like if we were up close. Again, we have the HR diagram to just kind of bring it home. The more massive the star, the faster it rushes along its track, and the higher up it ends on the main sequence. And we look again at these tracks. It takes maybe for something half the mass of the sun 150 million years to form from a cloud all the way down to a star. The sun might take 30 to 50 million years. Something more massive than the sun might take 3 million years. But something really massive might take 60,000 years. And upwards of the 30 to 50 solar mass stars take on the order of 10,000 years or less. So protostars themselves, just to summarize the entire thing, they take tens of millions of years to form for something about the mass of the sun. The central temperature goes from being extraordinarily cold to up to 15 million Kelvin. The density goes from being basically a couple hundred particles per cubic centimeter to 10 to the 21st times more dense and millions of times hotter. And the diameter shrinks by a factor of 100 million so that it can form a star. So stars start loose, something pops, they fragment, form protostars. Those protostars collapse under gravity, emitting their light. Eventually, they do some form of nuclear fusion, meaning deuterium fusion, but they don't do proton-proton chain until they finally get to 15 million Kelvin. And so protostars are the things that are formed from these giant molecular clouds, and we see these baby stars all throughout wherever we look. That's why we call the H2 regions star-forming regions.